Most people, if you ask them what NASA does, would give you the same answer. Rockets, astronauts, space, and they would not be wrong. But they would be missing most of the picture. Because the organization that puts people into orbit and sends rovers to other worlds is also the same organization studying the storms forming over your city, mapping the ice melting at the poles, and peering at galaxies that formed before our solar system existed. NASA is not one thing. It is many things happening at the same time, all pointed in the same direction. So what does NASA actually do? At its core, NASA exists to explore. That is the simple version. The longer version is that it exists to push the edge of what humans understand about space, about our own planet, and about the technology needed to go further than we have ever gone before. It was created in the late 1950s, at a time when getting anything into orbit at all was considered extraordinary. Today, the work it does covers everything from the surface of the Earth to the far edges of the observable universe. Human spaceflight is still one of the most visible parts of what NASA does. Sending people into space is not simple. It requires years of preparation. Astronauts training in aircraft, in underwater facilities designed to replicate the feeling of weightlessness, in simulators that recreate every system on a spacecraft down to the smallest detail. The missions themselves involve launching humans beyond the atmosphere, keeping them alive in an environment that has no air, and where temperatures swing between extremes that no equipment on Earth routinely has to handle. What those astronauts do once they get there, running experiments, performing spacewalks, maintaining equipment, testing how the human body holds up over long periods, produces knowledge that could not be gathered any other way. A large part of that work happens on the International Space Station. For over 2 decades, astronauts from multiple countries have been living and working in orbit, cycling through the station on missions that last months at a time. The research being done there covers a wide range of fields. Scientists study how the human body changes in microgravity, how muscles weaken, how bones lose density, how vision can be affected. They grow plants, study how flames behave without gravity pulling them in one direction, and run experiments in materials, science, biology, and medicine. The ISS is also a testing ground for technology, equipment, spacesuits, life support systems that will eventually be needed on longer missions farther from Earth. When a piece of hardware performs well over years of use in orbit, that is not just a result. That is evidence. Evidence that can be used to design the next generation of systems with more confidence and fewer unknowns. And those longer missions are what a lot of the current work is building toward. NASA has been focused on returning humans to the moon for the first time in decades. Not simply to visit and come back, but to develop a sustained presence. To learn how to live and work on another world for extended periods. The moon offers something no simulation on Earth can. It is a real environment with real gravity, real radiation exposure, and real operational challenges. Every lesson learned, there is a lesson that carries forward. The moon is a practice ground for everything that comes after it, including the much longer and more difficult goal of sending humans to another planet. While the human side of exploration gets most of the attention, robotic missions have quietly been doing extraordinary work for decades. Spacecraft have flown past, orbited, and landed on planets, moons, and asteroids throughout the solar system. Rovers have driven across the surface of another world, drilling into rock, analyzing soil, and sending back images and data that scientists are still working through. These robotic missions reach places that humans cannot yet go, and they go there first, studying the environment, testing technologies, and answering basic questions before a crewed mission is ever considered. Some of these spacecraft travel for years before reaching their destination. Some operate on the surface of another world for far longer than anyone originally planned. The data they send back, one signal at a time across hundreds of millions of kilometers, is some of the most valuable scientific information we have. Then there is the work that happens when you point instruments not at nearby worlds, but outward, toward the rest of the universe. Space telescopes have completely changed our understanding of what is out there. Orbiting above the atmosphere, away from the interference of clouds and weather, they can observe things that ground-based telescopes simply cannot see with the same clarity. Galaxies in the process of forming, stars in the final stages of their lives, vast clouds of gas and dust collapsing into new solar systems. The light from objects so far away that it left its source billions of years before Earth existed. This kind of astronomy does not grab headlines the way a rocket launch does, but it has produced some of the most important scientific discoveries of the past century. One of the less talked about but genuinely important things NASA does is point those instruments back at Earth. A large fleet of satellites orbits our planet continuously, measuring things that cannot be easily tracked from the ground. Ocean temperatures, ice coverage in the Arctic and Antarctic, the health of forests, levels of gases in the atmosphere, the path of storm systems as they develop and move. This data is used by scientists, by governments, by disaster response agencies, and by researchers trying to understand how the planet is changing. The satellite that tracks a hurricane as it strengthens over warm water before making landfall is doing work that saves lives. That is as much a part of NASA's mission as anything that happens beyond Earth's atmosphere. Behind all of this is an enormous amount of engineering and scientific work that never leaves the ground. Spacecraft do not appear ready to fly. They are designed, tested, broken deliberately to find the failure point, redesigned, tested again. Rocket systems are run through thousands of simulations before they are trusted with a crew. Scientists spend years analyzing data from missions that ended before some of them were born. Engineers develop materials and systems specifically because space requires things that simply do not exist yet and have to be invented. Much of what NASA does happens in laboratories and research facilities, on computers, in meetings between people trying to solve problems that have never been solved before. All of it connects. The technology developed for one mission often turns out to be useful for something completely different. The knowledge gained from studying a distant planet changes how we understand our own. The data collected from Earth-observing satellites feeds into climate models that inform decisions made on the ground. Nothing NASA does exists in isolation. What this adds up to is an organization that is genuinely hard to summarize in a single sentence. NASA studies our planet from above and other worlds up close. It puts humans into orbit and sends machines to places no human has ever been. It builds and operates telescopes that look back to near the beginning of time. It trains engineers and scientists to solve problems that will matter not just for space exploration, but for life on Earth. The rocket launches are real. The astronauts are real. But they are just the most visible part of something much larger. An ongoing effort to understand where we are, what is out there, and what it would take to go further. That effort is still going, and it is nowhere near finished.